Is Simon Ritter.
Okay, well, good afternoon, welcome. I'd like to just start with a quick show of hands. So who came to Mark Reinhold's presentation yesterday on JDK and JDK9? Okay, reasonable number of people. Well, that's fine, because clearly one of the things that he talked about was Lambda Expressions. And I came to that session as well because I was a little bit concerned because I didn't want to just basically repeat what he'd said. There is going to be a little bit of overlap in terms of what I'm talking about because you simply can't address Lambda Expressions without covering the same material to some extent. But I will be going into more detail and I will talk about some of the implementation details so that you can get more information around those sides of things. So the first thing I have to do is I have to put up our safe harbor statement to make sure that we are fully in compliance with Oracle ways of presenting. So I think you've had enough time to read that. So let's start with a bit of background to where we're coming from in terms of adding Lambda expressions to Java. I like to add a little bit of history to my presentation. So here are a number of reasonably famous people. And it's always interesting to see how many of these people you can actually recognize. I'm hoping that pretty much everybody will recognize the second person on the left. Anybody know who that is? Turing, yes, Alan Turing, good. So that's Alan Turing, who is clearly one of the most important people when it comes to the initial designs and development of software as we know it today. The person on the far left is Alonzo Church, and he is the one who wrote this book called Lambda Calculus, which is what a lot of the things I'm going to talk about in the rest of the presentation are really based on. But of course, his approach was not one from a programming point of view. He was doing it from a mathematical point of view. And the reason I put them together is because Alonzo Church was actually Alan Turing's supervisor when he did his PhD. So there's a lot of history there in terms of computing. So Alonzo Church came up with this concept of lambda calculus. Now, here's a question for you. Does anybody know why it's called lambda calculus? No, okay. Well, this is a bit of trivia for you then. The reason it's called lambda calculus is because when Alonzo Church first put together the theory around lambda calculus, he was basing some of the work he did on a thing called Principia Mathematica, which is a book that was written in 1910, and it is basically some fundamentals about mathematics. And so he wanted to base it on some of that work, and the typesetting that was going to be required was that the symbol X was going to have a line above it, and the typesetter couldn't do that. So the typesetter put a up hat before the X, and then the next typesetter looked at that and said, oh, I can't do that, so I'll put a lambda before it. So it then became lambda calculus, simply because it was supposed to be X with a line over the top, and the typesetting ended up with a lambda. Trivia for you. The third person is Haskell Curry, who was somebody who really did a lot of work in terms of what's called combinatory logic, and this led to the whole concept of functional programming. And we'll talk more about what we mean by that in terms of Lambda expressions and Java and so on. And then the next person is John McCarthy. He invented Lisp, so clearly going from a sort of a functional programming type of thing. He's also a very interesting person. Again, a little bit of trivia for you. I will move on from the trivia soon. In terms of trivia, he did a presentation at MIT in 1961 where he proposed an idea of having a utility model for time sharing in computing. So he was really the first person to invent cloud computing, because that's what we do now. So, and then finally, the last two people on the right are Gerald Sussman, who invented the scheme programming language, which is very like Lisp, and Guy Steele, who had a lot of input in terms of the development of Java. There's another programming language called Fortress that he developed, and he's done a lot of work in terms of parallel algorithms. This is where everything kind of comes together. So that's the history lesson. In terms of computing today, really the most fundamental thing that we're facing is the fact that Moore's law has continued to advance in terms of the number of transistors that we can squeeze into the same space. So we can make processors more and more dense in terms of transistors. But what we've not been able to do is to make the clock speed continue to rise at the same rate that we've increased the number of transistors. Physical laws like clock skew and the cooling of processors at higher clock speeds simply limits what we can do in terms of a PC or a laptop or whatever. So to take advantage of the extra transistors, what we now do is we create multiple core processors. So we have dual-core processors, quad-core processors, six-core processors. Even not laptop, tablets and mobile phones now have quad-core processors and things like that. And this presents us with a problem in terms of developing software, because we've been very familiar with developing software that works in serial. We have this concept previously of time sharing, where you could sort of flip between different processes to give you the kind of illusion of being able to run things in parallel, but they've not really been happening in parallel. Now you really can do that. And so if we're going to take advantage of these things, we have to figure out how to write code which works well in parallel. And that's not an easy thing to do. So from a point of view of Java, what we're doing is adapting all of the different parts of the platform in terms of helping you as developers to take advantage of parallel programming, multiple cores, and multiple processors. So we're changing the language, we're changing the libraries, and we're changing parts of the virtual machine to give us all of this advantage. Now, from the point of view of concurrency, Java as a language has always had the concept of multiple threads and concurrency built into it. Right from the very beginning, we had Java 1 with the thread class. The thread class gives us the ability to create a new thread of execution, have it execute a run method. We have the idea of synchronization primitives. So you can take a method and you can make it synchronized. You can take a block of code and you can make it synchronized, so that you can acquire the monitor associated with that object, and you can prevent other threads from using either the same method or the same block of code simultaneously. We also have various methods in the thread class, such as sleep, wait, notify, and interrupt, which allow you to coordinate the way that the threads interact with each other. But the problem with that is it's a very basic form of multi-threading and parallel coding. And it's very, very difficult to make code work reliably and accurately if you're using those kind of primitive ways of doing things. Move forward to Java SE 5, and to alleviate that problem, we introduced the concept of the concurrency utilities. JSR 166 was proposed, it was developed, and it added a lot of higher level functions, higher level capabilities that people who've done multi-threaded parallel programming are very used to. We introduced things like semaphores, which are well understood concepts. We introduced things like mutexes, read-write locks, all of those things which make it a lot easier in terms of developing multi-threaded parallel code, because you can take advantage of these things and have your threads coordinated and make them work together in a much more reliable way. Java SE 6, we added a few minor things to that. I say minor, things like phasers, those types of things, just to kind of add more capabilities to the concurrent utilities. And then in Java SE 7, we introduced the fork join framework, which was really about taking a problem that can be decomposed into a number of sub-problems, and that can actually happen recursively. So you can gradually make the units of work smaller and smaller until you get to a point where you feel that the unit of work being handled is something that can be allocated to a particular thread, and then it can go off and process it. Now that's been used very successfully in a number of places, and it's very well designed from the point of view of a task which can be decomposed into subtasks which are independent of each other. So if you're not sharing data between these subtasks, then the fork join framework works very well. As soon as you start getting shared data and you need to apply locking to it, then it's something which, again, needs to be addressed, and you need to think more carefully about what you're actually doing. But it's a very good framework in terms of making life easy from the point of view of not having to create a pool of threads, not having to worry about the coordination of those threads and synchronization and so on. it handles all of that for you. And then in Java SE 8, what we're introducing is Project Lambda, and we'll see what that actually means in terms of enabling us to make code more parallel and do it in a simpler, more straightforward way. So from the point of view of parallelism in Java, what are the goals that we're really trying to achieve? Well, we want easy-to-use parallel libraries. So we want a set of libraries that gives us functions and methods that we can use in a way that really isolates us, the developer, from all of the complexities that are involved in making things parallel. So we don't want to have to handle things like task scheduling. We don't want to have to handle a lot of the thread management, the load balancing, and so on. We'd like things in the library to do all of that work for us. And certainly if you look at the way code is written at the moment, and you write code for a serial type of problem where you're doing one thing after another, and you look at the way that you write code for a parallel problem where you're doing things simultaneously, they're really very different. So it would be nice if we could come up with a set of solutions where, whether it was a serial approach to a problem or a parallel approach to a problem, then you could really write the same code from a syntax and method point of view, and you don't worry about how it actually happens. So that really is a very big goal in terms of making life a lot easier. So the fork join framework was a good place to start. It really helped in terms of moving that complexity away from you, the developer, into the library. But we need more. We need more capabilities to enable us to write this parallel code. Now, primarily, what we're doing here is we want to talk about using libraries to do this, because this gives us a number of advantages. By using libraries, we are enabling you, the developer, to do things in the most efficient way. So you can get better time to market because you can evolve libraries faster than you can evolve a language. If you're creating a new set of library code, it's very easy to create a jar file and then just place that jar file as part of your application, and you can reference the code in that library straight away. You don't have to build those features into the language, which clearly takes a long time. By using libraries rather than changes to the language, you're decentralizing, moving away from the core of the language and giving more choice in terms of the library code that you use. So if you want to take a different approach, you're not tied to what's happening in the language level. You're able to change the library code without having to make big changes in terms of your coding. Easy to change libraries, very practical to experiment with them. You can try one library, then try another library, see which one works best. From a language change point of view, impact of those changes is significantly bigger. Learning the new capabilities of a language change is a significantly bigger thing than learning simply a new set of methods to call from your library. So that's what we really want to do, is we want to keep things at the library level and simply give you more classes and more methods to enable the development of parallel code. But sometimes we actually reach a limit where we do need some support from the language. We need some things built into the language that are actually going to help us to develop library code, which can then make things easier for you. So let's talk about bringing lambdas to Java. So this is where we get into a little bit of overlap with Mark's presentation. The issue that we've got is, how do we approach parallel code? So here's a very simple piece of code, and it's the kind of thing that we do a lot in Java. We do a lot in any kind of application code. What you do is you collect a set of data, and then you want to process that set of data. It's the good old input, process, output. Now, in this example, very simple example, we're using a set of students. So we collect data about a group of students in a particular country or a particular city or whatever, and then we want to process it. And from the point of view of this piece of code, what we're actually interested in doing is finding out what was the highest score that any student scored in a particular year. Okay, simple thing that we want to do. So we write a piece of code in Java. Java is Turing complete, so we can approach any problem. We know that as long as the problem is solvable, we can write code to do it in Java. Good. So we create our collection of students. We then give ourselves a highest score value to maintain the highest score, so as we go through the list, we know which is the highest score that we've found so far. And then we iterate. So we create a loop, for loop, we iterate over our collection of students, we look to see if a particular student graduated in the year that we're interested in, and then we look to see whether their score was higher than the highest score. Okay, very simple piece of code. Problem with that is that the moment that we have our double highest score, we are very restricted to the point where we can't make that code parallel in an easy way. Because having a single variable which stores the highest value means that if we have multiple threads trying to process the set of data simultaneously, that becomes a point of contention. We have to apply a lock to it so that multiple threads can't update it at the same time. Fundamentals of parallel programming. You have to protect mutatable data so that you can't have multiple threads accessing it at the same time. It's a race condition type problem. So this is not the most optimal solution if you want to make it parallel. It works fine in a serial environment, but trying to make it parallel is just not going to work. And the reason for that is that the client, which is our code, is controlling the iteration. So we've created a for loop, and it becomes inherently serial. We have this single variable that we store data in, and because that's being shared between a number of threads, it's not synchronized, it becomes unthread safe code. So we can't apply a number of threads to it in a very simple way. So we can take a different approach. Again, because Lambda is Turing complete, we can take the code and we can rewrite it using a different type of syntax, different approach. So here what we're going to do is we're going to actually chain together a number of method calls. So we're going to put these method calls together, so take one set of data, pass it through a method, pass that to another method, pass that to another method, and get the result. So now we end up with a set of inner classes. This becomes a little bit more functional in terms of its approach, and it also becomes more of a fluent API. It's not really a fluent API, because if it was a fluent API, then each method would be returning the same type. Similarly, if you've done functional programming, this is more monad-like, where we're decomposing a complex operation with multiple parameters into a number of operations that can be chained together. So what we do here is we take our collection of students and we say assign the value of the double score to being the result of this chain of operations. Now we've still got our value, but because we're generating that value from our chain of method calls, we're not having this single point which needs to be controlled and avoiding contention. So now we end up with a set of methods which do a filter, map, and then max, which is in effect a reduce. So our filter method takes a predicate. Predicate is in effect the condition that we want to satisfy to return the subset of the data that satisfies that condition. So in this case, we create an inner class which has a method called op, takes a student S as a parameter, and returns whether the graduation year was 2011. So that's a Boolean. We pass the result of the data that's been passed through that method to the map method. In this case, it takes a mapper method, mapper type, as a parameter. And then we actually have a method on that which is called extract, and that simply returns the score of that student. And then we pass all of that data into the max method to say, okay, give us whichever is the maximum value of that set of data. So now, the iteration, the filtering, the accumulation are handled by the library, which means we can take a different approach to how we do this. And if we want to, we can do this in a lazy evaluation way and have data being made available between the method chains so that we don't have to process all of the data before we pass it on to the next part of the chain. We can process some of it and then make that available so that we read in a lazy fashion, and therefore as we get further down the chain, in this case obviously we would have to read everything, but we could get to a situation where we don't have to evaluate everything if we were looking for a specific value. So we make it much more flexible in that way. It's no longer inherently serial because we don't have a single variable that we have to control and we have to apply locking to. It's thread safe. The client logic is completely stateless. So again, we don't have to worry about that. The problem with this is that it's not a particularly nice looking piece of code. Inner classes are syntactically, I'm going to use the word, syntactically ugly, because you end up with a lot of boilerplate code for a very small amount of code you actually want to execute. Clearly, in this case, we've got a small, simple example. If you were doing something more complex, you'd end up with a very nasty-looking piece of code that would be very hard to maintain. So this is where the concept of lambdas come in, or lambda expressions, so that we can simplify that. Rather than having an anonymous inner class that we create with a method which has the code that we want to execute in it, we effectively say, well, okay, let's have a filter, but then we're going to pass into that a lambda expression, which is in effect an anonymous inner class. It's an anonymous class method, anonymous method, I should say, not class. It's an anonymous method that we can pass as a parameter to the other method. So here we're saying for the filter, the parameter of the method that we're going to pass is student S, and the body of the method that's going to be executed is to evaluate whether the graduation year of that student is equal to 2011 and return a Boolean depending on whether that is true or false. Similarly, for the map method, when we call that, we use a lambda expression where the parameter of that anonymous method is student S, and the body of that method is simply to return the score of that student. This gives us much more concise code. Being more concise, it becomes more readable. It's a little bit more abstract. Certainly less error-prone because you've got less code, there's less boilerplate code around it, and so on. It doesn't rely on mutable state, so it's still thread safe. And it's a lot easier to make this parallel, because now we can look at this code and we can say, okay, leave it to the library to figure out how to process that method, leave it to the library to figure out how to actually make that happen in the most efficient way, make it happen in parallel, and so on. So some details about lambda expressions. Effectively, you can think of a lambda expression as being an anonymous function. So this is where we kind of get into the idea of a functional programming model versus the imperative object-oriented programming model that we use at the moment. So it is like a method. It has a typed argument list, so you pass arguments to it in the same way that you would any other method in Java. It has a return type, which may well be inferred by the compiler. So you don't actually explicitly have to make a return. If you think about the example, we had the idea of evaluating whether the graduation year of a student was 2011, but there wasn't an explicit return of that. So the fact that we executed that and that generated a Boolean, the compiler would infer from that that the return type of this anonymous function was going to be a Boolean. So that would give us the return type that we would use. And then you can also have a set of thrown exceptions if you want to. So you can throw an exception in a lambda expression. There's no issue around that. And you can also obviously have a body to your expression. So the code that you want to execute as part of your anonymous function. So we end up with the same set of code that we had before. So of course the question then is, what is the type of a lambda expression? Because if we're passing a lambda expression as a parameter to another method, it must have some form of type involved, because every parameter has to have a type. So in this case, what we're actually going to do is we're going to define that the type of a lambda expression is a functional interface. And all we're really saying there is that from the point of view of a functional interface, it is equivalent to an interface with one method. So a single abstract method type. So you can think of it as an anonymous inner class which has a single method that you implement. And that's what we're defining as being a functional interface from the point of view of our lambda expression. The way that these are identified is structurally. So the compiler will figure out what that type actually is in terms of its signature. So you pass in a number of parameters. There is a return type which could be inferred by the compiler. and there are various things like that. So what the compiler will do is, from that information, it will determine what the signature is, and therefore what type, as a functional interface, this actually is. And you can end up with a list of typical sort of Lambda expressions with a functional interface. So the comparator, because these are used a lot in Java, so comparator, file filter, directory stream, runnable, action listener, callable. All of these fit exactly into the idea of Lambda expression because they have a functional interface because they're single abstract method types. So we can think of these as being functional interfaces that we can use in Lambda expressions. So then we get the idea of target typing. So what we want to do is we want to say, okay, when you use a Lambda expression, what this is effectively doing is creating an instance of a functional interface. We know the type because we can determine that from the signature of the parameters and the return type of our Lambda expression. When we actually use the Lambda expression, what we're doing is instantiating an instance of the interface that we've determined from that signature. So that will be inferred from the context where it's actually being used. The compiler will handle all of that for us. And then it works in both where we assign the thing and also where we invoke it. So you can assign a value to be a Lambda expression, and then you can also then pass that variable as a parameter to a method and use it in that way. So you've got the assignment and you've got the invocation, both of which are determined by the compiler, and it will figure out what is the exact type to be used in that case. If there is some ambiguity involved, then you can actually use explicit casting to get around that. So we end up with the example that we see here, where we've got a comparator. In this case, it's typed as a string comparator. So we have a single method compare, which takes two strings. We then return whether the length or the difference of the length in those two strings. And we can then change that to being a Lambda expression simply by replacing it with the code underneath. Parameters being passed to the Lambda expression are the string x and the string y. The body of the Lambda expression, the anonymous function, is to subtract the length of y from the length of x, and that will return an integer. So we've got our signature for our anonymous function, so the compiler can figure out exactly what's going on. Then we have the idea of local variable capture, because it may well be that you want to access variables from outside of the Lambda expression, which are within the scope of where you're calling that Lambda expression. And that's quite valid. You can do that. But in the same way that you can think of a Lambda expression as clearly a replacement in many cases for an anonymous inner class, if you're using an anonymous inner class, you know that there's this issue that you can only reference variables from outside of the anonymous inner class if they are marked explicitly as final. So they can only be assigned once, they can't be changed. Reason for that is because we need to be able to copy them when we create the anonymous inner class and call that particular method. We don't want them changing as we're processing them in the method that's being called. So we mark them as final. In Lambda expressions, we allow you to refer to effectively final variables, which means that they don't have to be marked as final, but they have to behave as if they were marked as final, which means that, again, you can only assign a value to them once and it can't be changed. So long as you do that, as long as you have a variable where you assign it once and you don't change it, then it can be determined to be effectively final, and you can reference that within your Lambda expression. So here, we've got a simple example where you've got a thing that you want to pass in parameters for the file and also a timestamp. And then you're going to use a Lambda expression to say, was this file modified before the last modified time? Before is a parameter that's being passed into the method. We can infer that it is effectively final because it's not being changed in the code, and therefore we can use that as a reference within the Lambda expression, and that will work quite happily. There's no problem with that. We also need to think about lexical scoping, the scoping of how we reference other variables, and specifically the this reference. Because a Lambda expression is an anonymous function and can be thought of in the same way as an anonymous inner class, do we refer to this meaning the anonymous inner class that we're in effect creating, or do we refer to this being the this in the outer enclosing scope of the code? Well, what we do is we say there is no this associated with a lambda expression. This means the this of the enclosing code. So it will refer to the object of the enclosing code. Think of it as a predefined final variable. And so if we wanted to, we could refer to the this object as the enclosing code, and that would work quite happily as well. Type inference is very useful because what it allows us to do is to say, well, because the compiler can see a lot of information about what's actually happening in terms of the usage of your lambda expression, it can figure out various things for you. So in the case of our sort here, what we're doing is we're passing a lambda expression that takes two parameters, string x and string y, and then does something with them. But we know that in the case of this particular sort, there is some type information through the generic typing of a collection or something, which will tell the compiler that this collection holds strings. So if we're going to do comparisons on this, then we can only do comparisons on an object of type string. So we don't explicitly have to mark the parameters of our lambda expression as being of type string. We can leave that out. We can just simply put x and y, and the compiler will infer the type of those parameters for us. We're free to put the explicit type information if we want, but we don't have to do that if we don't want to. So all of it's inferred. We get the correct functional interface method signature generated because the compiler knows that it's string. This still gives us full static typing. Even though we're not explicitly putting the typing, we're not sneaking dynamic typing into Java. No, no, no. No dynamic typing in Java. And as it says here, it's a lovely, lovely thing, more typing with less typing. So it's a kind of joke you can only make in English because it has almost every word has the same meaning. So it's more about typing the type of an object with less typing of pressing of the keys. Now, the other thing that we can then do is we can make things a little bit more concise, less typing again. So what we're doing here is we're saying, okay, if you have a situation where you are calling a method as the body of your lambda expression, then we can make that simpler. Here we've got an anonymous inner class where we're saying, okay, this is a file filter, and what we want to do is we call the canRead method on the file object that's being passed into our accept method. Okay? Now, if we convert that into a lambda expression, what we can say is, okay, well, file f is our parameter that we're going to pass to the lambda expression. The body of that is f.canRead. Call canRead on f. So to make that simpler, what we say is, okay, well, we'll condense that a little bit more because it's effectively the same as saying, well, let's just say, okay, it's the file class, and we're going to call canRead on it. And because the compiler can infer all of the necessary type information, it can simply say that that is the equivalent thing. So what the compiler will effectively do is say file f as the parameter, body of the anonymous function is to call canRead on f and return the result. So it makes things a little bit more concise, a little bit easier to read. So if we put it all together, what we end up with is the idea of, okay, we go from a situation where we have an anonymous inner class, where we're going to use a comparator as, in effect, passing our function to the sort method. And the way that we want to do that is to implement the compare method, where we have two people, a person X and a person Y, and that is going to return the result of x.getLastName.compare to y.getLastName. So we're comparing the last names of the two people. We can convert that, so we can say, okay, let's turn that into a lambda expression. So now we get the collection sort on people as the first argument and replace the anonymous inner class with a lambda expression. The parameters we're passing in are person X, person Y. Body of the method is to run the same code, so we compare the last name of the first person and the last name of the second person. Obviously, we can make that a little bit simpler. So we can say, okay, let's just say comparing person P and P.getLastName. So again, this will allow the compiler to effectively replace that with a comparison between the two people. And we can make that a little bit, hang on, where are we? Yeah. So then we can simplify that further by using the method reference and say, okay, let's just say person.getLastName, comparing, and then finally we can just say comparing person.getLastName. And that just simplifies everything down so that we're making it nice and concise and easy to see exactly what's going on. So we're replacing a little bit of code, adding another method, and so on. So we end up with a situation where we're more concise, a little bit more abstract, but that's fine, much more reuse, and certainly more object-oriented in terms of the approach that we're taking. So Lambda expressions in Java have a number of advantages because currently the way that we handle aggregates in processing, which is groups of data, groups of objects, is through a for loop. That's typically the way that we process things. And so because that is inherently serial, we have a problem in terms of making it parallel. We need a different approach in order to simplify how we do these kinds of things. So we need some sort of internal iteration. We can do it through the use of anonymous inner classes, but we don't want to do it that way because it's too verbose, it's too unwieldy in terms of the syntax. So we need libraries which are going to handle the idea of serial and parallel processing in the same way. So we don't want to worry about, is it happening in serial, is it happening in parallel? And really adding Lambda expressions to Java, it's just no longer a radical idea. You know, it's just got to happen, so let's just get it done and allow people to use them. Which leads us into talking a little bit about library evolution. So we talked about the changes to the language. Let's talk about how this impacts on the idea of what we can do with libraries. So the real challenge with the libraries is that if we add Lambda, we are adding Lambda expressions to the Java language. So how do we take advantage of those? Certainly, if we'd had something like Lambda expressions from the very beginning when we first started writing Java, the class libraries as they are today would look very different because we'd obviously be able to take advantage of that, and so we'd have very different looking code. And what we're faced with as Oracle is that if we add Lambda expressions to Java, we kind of highlight some of the age of some of our libraries. But certainly, if we don't change the libraries to take advantage of this, then it's really like, it's not giving us a great deal of improvement in terms of the library. So we really want to make sure that we do that. But we are faced with a problem. We're faced with a problem that we need to change a number of the APIs to take advantage of this. Because if we're going to allow the use of Lambda expressions, anonymous functions throughout the library code, we need to add more methods to a number of the libraries. So things like the collections. Collections are based on an interface, well-defined interface. And what we're saying is that in order to allow you to use Lambda expressions in the best way, we need to extend that interface. So we've got two choices. We can either add methods to the interface, or we can subclass the interface and extend the interface that way. Neither of which are a good solution, because it means backwards compatibility is going to be a bit of a problem. Because if you start trying to add methods to an interface, you're going to break backwards compatibility in a significant way. So, what are we trying to do here? Well, the requirement is we want to aggregate operations on collections. It's this whole thing about replacing the use of the for loop with some library that enables us to process things in either a serial or a parallel way, which is invisible to the person writing the code. So we need new methods on collection for bulk operations. We need things like filter, we need map, we need reduce, for each, sort, and so on. And then what we can do is we can run these in parallel. One of the things that is also being added to JDK8 is this idea of a stream class. What that enables us to do is to say, okay, well, all of these methods are going to return a stream class, or stream object, I should say, stream class, stream object. So all of these things are going to return a stream object, and that's where we start getting into a more fluent API. So we can mix and match these things in whichever way we want. We can add as many of them as we want in terms of the chaining of the processing. And a stream object is simply something that returns a potentially infinite set of values. How it does that is entirely up to what generates that stream. So it can do it in a complete way where it generates all the values before it passes them on, or it can do them in a lazy evaluation way. And that's where we start getting into some of the real value in terms of making it easy to write parallel code. But the problem is, this is problematic. So we can't just simply add new methods to an interface without modifying places where people have used them before. So if I say to you, has anybody here used a collections class? Yes. So if I said to you, you've got to go and rewrite all your code that uses collections class, you're not going to be very happy, I'm sure. So we need a better way of doing that, okay? We can't control all the implementations, so if we had a situation where somebody gave us a jar file and we tried to reference that as a collection and we'd got some method that we were calling that was part of a new interface, we couldn't do that because it would break. So what do we do? Well, the simple solution is to add virtual extension methods, also known as defender methods in some places. So what we do is we specify them in the interface. We're adding new methods in the interface, but from the caller's perspective, this is just an ordinary interface method. So they don't have to worry about doing anything clever. Simply saying, okay, right, I want to call filter, I want to call map, I'm going to do that. But if somebody's already created a class which implements the collections interface and doesn't have the filter or the map method, then what do we do? Well, what we do is we say in the collections class, we will provide, collection API, we will provide a default implementation, something that will fill in the blank if it's not available. And that way you don't get runtime exceptions because you can't resolve that method because it doesn't exist in the class that's being compiled. So we end up with a situation where we've got a list, where we can have a sort, and we've got a default implementation of that simply to return the values that we want. So it gives us a way of extending our interfaces without having to worry about the implementation not being available in older versions of the class. But, okay, so stop right there. Isn't this kind of a way of sneaking in multiple inheritance into Java? Because now we've got an interface, and suddenly we've got an implementation in an interface, which is then being bolted into Java. And so, okay, if I extend one method and I implement an interface which happens to have an implementation of a method in there, well, that's kind of like multiple inheritance, isn't it? Because I've got one version coming from here, one version coming from there. Well, the reality is that Java has already had multiple inheritance. You have multiple inheritance of types because you can do extend one class and then implement another interface. So that gives us multiple inheritance of types. What we're now adding is multiple inheritance of behavior. So what we're saying is, okay, we'll add some methods in here, but because it's still an interface, you don't get instance variables associated with that. So we're adding behavior, but we're not adding state. So we don't have the idea of true multiple inheritance. True multiple inheritance in the C++ way of doing things involves having a full class where you have state and you have behavior in the form of methods. So it's a way of sneaking in some extra functionality that we need without really doing multiple inheritance, which is good because we don't want to do multiple inheritance. At least I don't want to do multiple inheritance. Let's have a look under the covers then, or under the hood, of what this actually is in terms of the implementation of lambdas. How does it actually kind of work? Well, we've got a number of different approaches that we can take to how we actually take a lambda expression and generate a set of bytecodes which are going to be the class that we generate. By definition, we have an anonymous function. An anonymous function, remember, is a single abstract method type. So we could simply replace all of our lambda expressions with an anonymous inner class with a single method which we implement the body of the code in. We specify the parameters, we specify the code, and we can simply map one to the other. So that's a simple, straightforward approach, okay? We can just replace it with anonymous in a class as a part of the pre-processing of the compiler code, or the code pre-processing by the compiler, and then generate bytecodes from that. We could do it in a different way. We could use method handles to reference the objects that we actually, or the classes that we want to use. We could use some sort of dynamic proxy, or we could use Invoke Dynamic. Okay. Well, anonymous in the class, okay, so direct compiler translation, we take our Lambda expression, we create anonymous in a class which has the right type, it has the right set of parameters, it has the right return type, the right body of code, everything is great. When we capture a Lambda expression within the code, what we need to do is invoke the constructor on that. So we've got the definition of the Lambda expression, which gives us a definition of our class for the anonymous function, and therefore when we capture a Lambda expression, we simply invoke the constructor on that. We have one class per Lambda expression, which is not nice because obviously if you've got lots of Lambda expressions, you're going to end up with lots of different classes generated by your compiler. It also burdens the Lambda with some form of identity because we have to generate a class, in this case called student reduced $1. So now it's got an identity. And if you're calling it an anonymous function and you give it an identity, it's not really anonymous anymore. So it's not quite right in that respect. And the other thing is it doesn't give us any improvement in performance. We're still doing the same thing as if we had written the code using an anonymous in a class, and so we don't gain anything from a performance point of view. Okay, so how about if we use method handles? So what the compiler is going to do is convert the Lambda body into a static method. So that's fine because we're not generating a new class for every Lambda expression that we have. So we generate a static method, and what we can do is we can say, okay, for the parameters that we have defined in our Lambda expression, we simply add those as parameters to our static method. We make the body of the static method the same as the body of the Lambda expression, everything works. If you reference variables from outside of the Lambda expression in the enclosing scope, then what we can do is we can prepend those variables to the parameter list that we're passing to our static method, and therefore we can use those without any problem. As long as they're effectively final, we don't get any problem. We can then do some currying where we can actually separate this out into a number of single parameter methods, I should say, single parameter methods, and get everything working quite happily. And then if you want to actually invoke that, where you've got your reference to your Lambda expression where you actually want to use it, all we have to do is use the method handle invoke method that's part of Java SE 7 and say, okay, invoke that static method. That's going to work. Okay, great. That's a different way of doing it. Might work quite nicely. Well, there's some issues with this. So basically, whatever translation we're going to use at this point is not just an implementation, but becomes part of the binary specification. It becomes part of the way that the bytecodes are generated. And if we wanted to change that at some later point, what we're doing is breaking, potentially, not backwards compatibility, but it's making things different. So you have one class that's being compiled with an older compiler, gives a different result to one version that's being compiled with a different compiler. Method handle API, is it ready to become a permanent part of the binary specification? Well, chances are it still needs a bit of work, so maybe we can improve performance on that, and so things are not quite ready for that. So performance of raw method handles compared to anonymous inner classes, is it better? Is it worse? Still not quite sure on that one. So translation options, how about if we start with an inner class and then switch to method handles later? Okay, well that's where we get the problem of older compiled classes still have the inner class implementation, we're not able to take advantage of performance improvements and so on. So we need some kind of fixed solution. Fixed solution has to be where we allow the thing to do the same thing every time. Problem is, old technology in the form of anonymous inner classes is not really good enough. New technology is not quite mature enough in the form of method handles. So what do? The answer is Invoke Dynamic. So we use Invoke Dynamic in terms of enabling us to have a recipe, in effect, for constructing a Lambda at the capture site. What this will enable us to do is say, okay, we create a declarative recipe, not an imperative recipe. So we're not actually putting the implementation in there, we're simply putting a reference to how that's going to happen at runtime rather than at compile time. Static bootstrap code becomes a Lambda meta factory, which will enable us to generate whatever code we need at runtime by calling that meta factory. When we first capture, we can then have a strategy that we choose and we link the call site through a method handle that's part of the Invoke and use Invoke Dynamic. And then subsequent captures, we can potentially change the way that we implement how we're going to do things, because we're using the method handle, we're using Invoke Dynamic, and we can change that in the same way that if we were using a dynamically typed language, the method signature changes and we need to change which method we're pointing to. By changing the reference in the method handle, we don't have to change the way that we invoke that method. We simply invoke it through the method handle and go somewhere else. Same thing with a Lambda expression. So the performance costs associated with how we implement the lambdas. Am I doing for time? Oh, have I got 10 minutes? 1 minute, okay. I thought I had 10, okay. Anyway, yeah, so there's 3 costs associated with a lambda. There's linkage cost, which if you think about anonymous in a class is really loading the class. There's capture cost, which is in the form of anonymous in a class is calling the constructor. And then there's invocation cost, which is calling the actual method that you want to use. So really, if you want to optimize things, you want to do the thing that's going to happen most. So that's the invocation cost. Code generation strategy. So what we can do is we can convert basically a Lambda definition to a static method. And what we can then do is say, okay, that becomes a piece of code as a static method. I'm going to have to move over this a little bit quickly, I'm sorry. And then what we can do is we can say, okay, where are we? That one. Okay. So at the point that we actually use the Lambda expression, we generate an Invoke Dynamic method, an Invoke Dynamic call to the meta factory. We have some static arguments, we have some dynamic arguments. The dynamic arguments are the ones that you're passing from your Lambda expression, the ones you see in your code. The static arguments are the ones that we would use in terms of the Invoke Dynamic. So in Java code, we can't actually represent this, so I've just put the red italics. Indy is the Invoke Dynamic. So we pass in some bootstrap method as the meta factory. We use a set of static arguments, which are the things that we reference from the Lambda expression definition into the right way to execute the code. And then that gives us a way of having different runtime translation strategies. So we could generate an inner class dynamically. We could generate a per single abstract method wrapper class. We could use that and do it that way. We could use a dynamic proxy. We could use method handle proxies.asInterface instance and call it directly that way. So that there are different approaches we can take. But because we're not tying ourselves to that at compile time, we can modify that at runtime. And that gives us the ability to improve performance at runtime. So just to conclude then, basically we need Lambda statements for a number of different reasons. We want to improve the existing libraries. We want to improve the way that things can be done in parallel. We want to make sure that there's compatibility with evolving interfaces for the idea of extension methods and so on. And we need to do that in the most efficient way as possible. So we need both language features, we need VM features in the form of Invoke Dynamic, and by doing all of this, it should make life a lot easier for developers in terms of writing parallel code, making the libraries do the hard work for you. So hopefully that's given you some more information about Lambda statements. Thank you very much.